looking at problem 347, top K frequent elements. So as per usual, the 3 steps of implementing any problem are 1, understand it, 2, visualize, and then 3, implement it. Given an integer array nums and an integer k, return the k most frequent elements. You may return the answer in any order. Here an example, we have 1, 1, 1, 2, 2, and a 3. K is 2, so we want the 2 most frequent elements. And just with the cursor you look, we can see there's 3 1s. So that's the first one, and then there's 2 2, so that's the second one, and that should be your output. Example 2, just a very basic example. We have exactly one number, k equals 1, we output 1. Like the constraints, there's between 1 and 105 numbers. Each number is between negative 104 and 104, and k is in the range of between 1 and the number of unique elements in the array, and it is guaranteed that the answer is unique. And here we also have a follow-up. Your algorithm's time complexity must be better than O n log n, where n is the array size. So there's two approaches to solve this problem that I know of. The first one is using heaps. The problem with heaps for this particular problem is that it does have it is an O n log n time. So it is a good algorithm in general. And if the problem was just for finding the most frequent element, then it would be faster. But because it's top k, and the constraint is that k is between 1 and the number of unique elements in the array, it is possible for it to just the end result to just be a heap sort algorithm where you just traverse the entire array, at which point it's n log n. So with that in mind, let's do the approach that's actually that can actually happen in linear time. And so let's take a look at the numbers here. So we have these 1, 1, 1s. And here let's keep tabs. Says your frequencies. So we're iterating. We see and let's see. So 1 is starting off. 2 is 0. We have 3 numbers. We're tracking number to frequency. So we just iterate over each one. 1. That's 1. It's another one of those guys. Now for 2 we see 1. Here we see a second, and then 3 we see 1. So like this is just you need to do this, like whatever approach you take, you need to just count the frequency of each number. And the question then becomes how can you without sorting your numbers or your key value pairs in any way, like still give out the k most frequent elements. So that's where the magic happens. And let's just let's first implement what we've done so far of just getting our frequencies, and then let's discuss how to just return the k most frequent elements. A map, let's call this a frequency map, just like we did. New map, and then we iterate over numbers just as we iterated earlier. And let's see if fric map dot has num, like we've already looked at this number before, we just add to it. Otherwise we set it to 1. Oh, and then sorry, set that guy to that, and then this guy to just 1. Okay, so that's how much we've reviewed so far in our examples and our visualization. And now we have to think about this interesting JavaScript quirk, which revolves around how arrays are unbounded. So let's look at well, let's create an array. Actually, we'll create it over here. Array is just an empty array, and let's take the frequencies and make the indexes of the frequencies, make the frequencies into indexes, and then the values into these numbers. And so, example 1, 3, so that's the frequency, is equal to this 1. In the case here, our frequency is 2, we make this equal to 2. And then our frequency here, 1, is equal to the number 3. Now look at how our array looks now. So we've actually expanded the array. We didn't have any problems. We said now its length is now 4, and it has this empty value. And we can take this property of JavaScript, and what we're gonna do is we're gonna move all the frequencies. We're gonna do this exact same process of filling up an array with the frequency indexes mapped to their number values. The one more thing is imagine we also had 4 and 4. Then we would actually see the number 4 is frequency is 2, and we see that these two overlap. So 0, 1, 2, its value is 2. We don't want to override it with 4, so we can use a different data structure. Instead of just a single number, we can do a set and just have sets for each of these, and that will solve. So I can just show you what the set example looks at. R is that, and then we would say R, so start from the beginning, R3 equals new set, add 1. Then we look at the next guy, R2 is equal to new set, add 2. Look at the next guy, the frequency is 1, R1 equals new set, add 3. And then we look at the last guy, so this is R2, so this guy already has a value, so we can say R2 dot add 4. And oh shoot, I didn't add to our, oh it's okay. I created a new set, but you can see I overwrote the previous array, but you can see what it looks like. So 3, then we have these 2, 2, 4, and then 1. And at that point, because they're already sorted from largest to smallest, we can just go back until we've k number of elements and just return those, and we are done. So let's implement what we just described. So we have the frequency maps, and we want to create our our set array, and we want to say for let key value of our frequency map if set r if this already exists, then we can set our value dot add key. So that's exactly what we did down here. We just added 4 in that case. Otherwise, set r equals new set key dot add just new set dot add key. Oh, okay, there we go. And you can see what this looks like. It should look the same as what we already did. And what example did we run? Let's use this guy. And there you have it. So you have this 3, and then if I were to add the 4s that we did in the second example, I guess we can't use that for this example, but you can see that we have these sets. So at this point, we just need to iterate over our sets until filling up our result and return our result. So we need to iterate k number of times, and then we are out. We're out of here. For let I equal, and remember we had to start from the right hand side, because the further you are to the right, the larger number of frequencies you are. Set r length -1, I is greater or equals to 0, I minus. So we say, so remember that we have these empty items. So we want to clear those guys out. And there's no set ri. Just skip over that. But now we actually do have a number. So result.push set ri. And then we want to say if how we already exhausted the k number of elements, like how do we already have k elements in the array. Let's ask that question. Result.length is greater or equals to k. We want to stop adding stuff to our array. Let's just call it quits. Let's see if this guy runs. So that passed. Example cases. Submit. Okay, and there you have it. That's the first approach with the unbounded array approach. Now let's look at how we would solve this with a heap, like a heap strategy. So this is it won't perform as well, but it's still good practice to know how to do heaps. So as a reminder, a heap is a data structure where it's an array, but it's in we think about it and treat it like it's a binary tree. An example, again, if you don't remember. So the array 1, 2, 3, 4, 5, 6, 7, 8, we represent it as a binary tree. So the first thing you need is so the key element of a heap is a heapifying function. And as a big summary of what we're going to do is we're just going to add our heapifying function that churns arrays into heaps. As a reminder, a heap is it could be either max heap or min heap. This is an example of a min heap because the root node is the smallest value. Max heap would be where the root node is the largest number. We are going to do max heap because we're only really interested in. We want to do a max heap where the numbers with the highest frequencies are at the closest to the root or at the root of the tree. And so yeah, we're not concerned at all with min heaps, only max heaps. And we need a heapifying function, and all you need to do a heapifying function, you need the array, and you need the index value, and you need to know how to grab know what the left and right node of the tree is. And so I won't describe this in all detail. Like if you're really interested, like definitely check out our video on sorting algorithms using the heap sort algorithm. So let me just assuming you know that, I'm just gonna write what we have to do. I'm gonna try to not make this video too long. X times 2 plus 1. That's right equals left plus right. Let largest equals index. We need to bound our heap. Let heap boundary equals. So what will this be? So we do need to know like how many unique items there are if you want to use the heap sort approach. So let's quickly grab that. So unique nums equals frequency map. How will you get that? So we have, I guess it's just frequency map that keys are the unique numbers, and then we say nums the length. And the reason we need the heap boundary is that as we, like in any good heap sort algorithm, at a certain point, like you're gonna have your numbers at the perfect position. Like the largest number will be at the right of the array, and you don't want to accidentally run your heapifying function on that number and reintroduce it into the array. So we need to set up like a boundary where our algorithm no longer runs to keep those numbers safe and locked in. So if left is less than our boundary and freq map dot get, will this be that get our left is greater than freq map dot get our largest, then that means that we actually have a number that has higher frequency. Largest equals left. And do the exact same thing for the right side. And then, as any good heap function would do, if largest does not equal index, then we need to do a swap. Let's define a swapping function. Left, right, r constant temp. This is just boilerplate stuff. R right equals r left. Oh, it should be the other way around. And then r right equals temp. And then let's call that guy. So we pass our array, and then largest and index. So we swap them, and then we need to just check all the inner nodes to make sure that they're nicely heapified as well, because we did this change. We need to compare against our the value that we swapped out. So that's the heapify function, and the only distinction here between here and a heap sort algorithm is that we want to just compare the frequencies. We don't want to get compare the actual numbers, because the numbers themselves aren't relevant. And so at this point we're just simply writing a heap sort algorithm. It's a two-step process. The first step is to run the heap sort algorithm from right to left, and what that will do is that at the end of doing that, the largest number will 100% be at the leftmost spot at index 0. And then the second step is we take that value, we swap it with the rightmost number, and then we move this heap boundary down 1 to lock it in and protect it from ever being heapified again. So we'll basically be sorting the array, and then we'll grab the k elements, the rightmost side of the array, and then call it quits. For let I equals unique. So we should, at this point we should probably let me just log this to double check something. Unique. Okay. So let's actually make this a full array. Like we're done with treating it like a different type of data structure. Let's just keep it simple with an array. Okay, so for let I equals unique nums.length -1, so that'll be the rightmost number. I is greater or equals to 0, minus. Then we need a max heapify our array, and our array will actually be unique nums, and it'll be I. So that will, and you can see that the rightmost number will be the one with the highest frequency. Left +1. And let me just hello. Yeah, okay. So yeah, there's the 1 is at the rightmost side, and 2 is there next. So this is looking good. And now we need to grab the leftmost number, move it to the right, and close down our bound. And then so that for let I equals nums.length -1, I is greater or equals to 0, I minus. So we want to swap unique nums. We want to swap the left and right, 0 with I. And we want to close down our heap boundary. And then we want to, because the numbers may have changed, and like that rightmost number isn't necessarily at the right heap spot. Let's heapify that guy. Unique nums 0. And then we can just return unique nums dot slice unique nums of length -k, and let's see how that does. Because that example, I think we have these examples, and let's And there you have it. We have implemented this with a heap, and we have implemented this with using an unbounded rectangle strategy. So thank you, and catch you later.